Well, we've come to the heart of the course. In this unit, we will be talking about a theory of the modern nanoscale MOSFET. In the last unit, we talked about charge, and current is charge that flows. In this unit, we'll talk about how that charge flows through a MOSFET under small drain-to-source bias and under large drain-to-source bias. We're going to use a particular approach to charge transport called the Landauer approach. So this is a very simple and intuitive way to describe electron transport. It works in very short MOSFETs where the transport is ballistic, and it works in very long channel MOSFETs where the transport is diffusive. So our description of this approach is going to be very simple and intuitive. There's a lot more that could be said. Those of you that are interested into diving deeply into the understanding of charge transport, electron transport at the nano and molecular scale, I can refer you to this textbook by my colleague Cipriano Datta. All right, so this is our picture of a nano device that's going to become a MOSFET for us. We think of a device then as having two reservoirs of electrons. The first one will be our source contact, and the second one will be our drain contact. These are reservoirs of electrons that are very close to thermal equilibrium. Large reservoirs with lots of scattering that maintains equilibrium. The device connects the two reservoirs. So that's our connection that allows charge to flow, electrons to flow from the source to the drain or vice versa. So our question in this unit is, how do we describe the flow of current, the current that flows in contact 2, and how does it depend on the voltages that we apply to these two contacts? We will assume that the two contacts are at the same temperature. Well, this is our current equation. So it's a simple equation, and we'll talk a little bit about the parameters in this equation. There are some fundamental constants out front, charge on an electron and Planck's constant. There's a quantity called the transmission, which is simply a number between 0 and 1. There is a quantity m of e, which we will call the number of channels, or also called the number of modes at an energy E. And then there are the Fermi functions of the two contacts. And at a particular energy, current only flows when the Fermi functions of the two contacts are different. That's called the Fermi window. And we do an integral over energy and add up all the contributions at the energies in the conduction band or valence band, depending on whether we have an N-channel MOSFET or a P-channel MOSFET. Now, this expression can be derived rigorously. For example, we could derive it from the Boltzmann transport equation, but we're going to see that it's intuitive and easy for us to use, and we'll just make use of this equation. Let's talk about some of the parameters in our current equation. The first one is the transmission. So the transmission is simply a number between 0 and 1. If an electron is injected from the first contact into the device, the channel of our MOSFET, the transmission T is the probability that it will transmit across and come out and exit in contact 2. Now, there's also a probability 1 minus T that it will backscatter and return and go back to the source from which it came. We're going to assume that there's no recombination in this device. The electron doesn't disappear. If it's injected, it either has to come back into the first contact or it has to go exit from the second contact. Same thing happens if an electron is injected from contact 2 and transmits across to contact 1. So simply a number between 0 and 1. Now, the transmission is going to depend on how much backscattering there is, because the scattering is what makes it hard for the electron to get across the channel and out the other contact. So the critical parameter here is lambda, the mean free path for backscattering. This is the average distance between scattering events. Scattering because of some type of impurity, charged impurity, lattice vibration or phonon, or maybe roughness at the oxide-silicon interface, whatever the mechanism is that might scatter the electrons. Now, what do we mean by ballistic transport? In ballistic transport, the length of the device is much shorter than the average distance between scattering events. So virtually all of the electrons that are injected from contact 1 simply transmit across and leave from contact 2. So T is equal to 1. This is what we mean by ballistic transport. Now, at the other limit, the channel length or device length is many mean-free paths long. The mean-free path is very short. There's a lot of scattering. An electron that's injected from contact 1 undergoes some kind of random walk. There is some chance that it will exit into contact 2, but the transmission in this case will be much less than 1. Most of the electrons that are injected will turn around and come back into contact 1 from which they were injected. This is the diffusive limit. In general, especially these days with modern technology, we're somewhere between these two limits. Okay. All right, there's a very simple equation that tells us, that relates the transmission to the average distance between scattering events. It's simply the mean free path divided by the mean free path plus the length of the device. Okay, so this expression we can derive again from the Boltzmann transport equation. It tends to work very well in practice under most conditions that we're interested in, but it's also very sort of intuitive. At least we can see that it makes sense in the two limits. So for example, in the diffusive limit, where the device is many mean free paths long and there's lots of scattering, this expression simply reduces to transmission is the ratio of the mean free path to the length of the device, and that's much less than 1. In the other limit, the device length is much shorter than a mean free path, and this expression reduces to 1. That's the ballistic limit that we talked about. So this expression works from the diffusive limit to the ballistic limit, and it works in between. I do want to point out, and it's just one subtlety that we need to be aware of, that the mean free path is not simply the velocity times the scattering time. That is what is often called the mean free path. We'll denote it by a capital lambda, and that's a perfectly good mean free path, but it's not the one that we need here for discussing current flow. I can illustrate that in a simple example in one dimension. Let's say we have a nanowire MOSFET, and electrons can only move in the plus x direction or the minus x direction. And let's say an incident electron encounters some type of scattering event, a lattice vibration or whatever. And let's say that this scattering event is isotropic. It has equal probability of knocking the electron in any direction. And in 1D, there are only two directions. It could scatter forward, or it could turn around and it could reverse direction and backscatter. We refer to this as the mean free path for backscattering, because the backscattering events are the ones that reduce the current. So you can see in this case, if we forward scattered, it's as though we haven't scattered at all. So basically, in this example, it takes 2 scattering times on average to turn an electron around. So our mean free path for backscattering would be twice the velocity times scattering time, or twice this conventional mean free path. The bookkeeping gets a little more complicated in 2 dimensions and 3 dimensions because of the angles involved, but you should just recall that there is some numerical factor that multiplies the distance between scattering events and gives us our mean free path for backscattering. Okay, now, what is a channel? So channels are like lanes on the highway. They carry the flow of automobiles on a highway. They carry the flow of electrons in our semiconductor device. So we can illustrate what a channel is in a simple one-dimensional example. So let's say we have a band structure, an E of k in 1 dimension, and we'd like to understand what a channel is. Well, It's related to the density of states because there has to be a state to hold the electron. So if I ask how many channels are there at energy E sub 1, well, I can see that there's a state at that energy. So, and that state has a velocity because the velocity is the slope of E of k. So I have a state with a velocity so the electrons can move in that state. That's a channel. In one dimension, we know what the density of states is. We know what the velocity is. If it's a parabolic band, 1/2 mv squared is equal to energy. And we can deduce what the number of channels is. It's it takes a little more work to generalize it to 2 dimensions and 3 dimensions, and then we need the average velocity in the direction of the transport or of the MOSFET channel length or whatever. But the basic idea is this: a channel is a state with a velocity. So for parabolic bands, you may remember that in 1D, the density of states goes as 1 over the square root of energy. In 2 dimensions, it goes as independent of energy. And in 3 dimensions, it's the square root of energy. Now, velocity for a parabolic band, velocity goes as the square root of energy. So in 1D for parabolic bands, the number of channels, as long as I'm in the conduction band or valence band where there are states, the number of channels is independent of energy. In 2 dimensions, it'll go as a square root of energy, and in 3 dimensions, it'll go linearly with energy. Okay, so that's our energy-dependent number of channels. So we've talked about some of the key parameters. We've talked about transmission, and we've talked about number of channels. In 2D, we would multiply the velocity times the density of states in 2D, which is independent of energy. And this would be our expression for the number of channels versus energy in 2 dimensions. We're assuming here that we have a parabolic band. We have large structures. In very small structures, you can actually count individually the channels. And that leads to some interesting effects we'll discuss in a minute or two. The mean free path remember I said there's a numerical factor that multiplies the average distance between scattering events. In 2 dimensions, when you take out that averaging over angle, the mean free path for backscattering is pi over 2 times velocity times scattering time. Okay, so we have simple expressions for transmission and for number of channels, and we will be able to use these to work out transport in our MOSFETs. Okay, and we have expressions for the mean free path as well. Now, the final quantity in this expression is what we refer to as the Fermi window. The Fermi window is the range of energies for which the Fermi functions in the 2 contacts are different. That's where the current flows. If F1 minus F2 is non-zero, then we'll get a contribution at that energy to the current. So let's see how this plays out in practice. This actually gives us a very simple physical picture for how current flows in a small device. So my device, let's say it's characterized by some simple band structure, some parabolic E of k, for example. Contact 1 has a Fermi level EF1. If we apply a voltage to contact 2, we know that voltage pulls the energies down. A positive voltage will lower the Fermi level in contact 2. So now we have 2 different Fermi levels in the contacts. If we look at the states in the device that are below EF2, they're also below EF1. This is simplest to think about at T equals 0 Kelvin, where all the states below the Fermi level are filled with probability 1, and all the states above are empty. So below the lowest Fermi level, F1 is equal to F2 is equal to 1. So F1 minus F2 is 0. Those states give us no contribution to the current. Above the highest Fermi level, the states are empty for both EF1 and EF2. So F1 is equal to F2 is equal to 0. F1 minus F2 is 0, and there's no contribution to the current from those states. The only states for which F1 does not equal F2 lie between the 2 Fermi levels. This is what we refer to as our Fermi window. So if we look at a state between the two Fermi levels. Well, if that state is empty, then contact 1 looks at that state and says, that's below my Fermi level. That state should be filled. So the first contact will send an electron in to fill that state. Well, then contact 2 looks at that state and says, that state is above my Fermi level. It should be empty. And therefore, the electron flows out into contact 2 to empty that state. That leads to a continual steady state flow of electrons in from contact 1 to fill the state, out into contact 2 to empty the state, and that represents a current that flows into contact 2. That's our simple physical picture of how current flows in a nano device. So to summarize, this is the current equation that we're going to apply to MOSFETs. We've tried to talk about the key quantities in that expression, the transmission, the number of channels in the Fermi window. This can be used to describe current in small and large devices, in devices that are much shorter than a mean free path, and devices that are much longer than a mean free path. In the next lecture, we will take the first step towards applying this current equation to MOSFETs. So we'll see how this current equation simplifies for low voltage between the two contacts, and we'll see how this current equation simplifies when we have a high voltage between these two contacts, which are going to represent the source and drain of our MOSFETs. So we'll continue the discussion in the next lecture.